Okay, thank you. And I don't have anything prepared for this session because I found out today that there is this session in a reminder email. But I skipped talking about the secondary normalization group method in my lecture. So I'll talk about SRG method. Oh, sorry. Okay. Okay. And the second renormalization group method is an improved TRG method. Sorry, and the SRG method was originally proposed on honeycomb lattice tensor network. And TRG was can be also defined on honeycomb lattice. And on the honeycomb lattice, the tensor is rank 3 tensors. So the two rank 3, this M is made of two rank 3 tensors. And in the TRG on honeycomb lattice, this M is decomposed into two rank 3 tensors. And the TRG for honeycomb lattice tensor network is formulated by repeating this decomposition again and again. But this decomposition is locally carried out. So the information of environmental tensor is just ignored in this decomposition. This ME is the environmental tensor, meaning that M is removed from the whole of the network. So the ME environment tensor ME contains many tensors and many tensor tensor contractions. So actually, it's difficult to obtain ME exactly. So instead of ME can be approximately evaluated by tensor renormalization. And this figure shows a tensor renormalization for environment tensor ME. And repeating this tensor renormalization for environmental tensor, this ME is approximately obtained. Once ME is obtained, this ME is obtained. So the influence of the environmental tensor is included into the decomposition of M. And so this decomposition, the decomposition of rank 4 tensor is locally carried out, but in this sense, the global information can be included in this local decomposition. So the accuracy of numerical results is improved by second renormalization group method. And for square lattice tensor network, the environmental tensor DE is rank 4 tensor. DE T is rank 4 tensor, and T is removed from the whole tensor network. Then this the rest of tensor network, removing a single T, is environmental tensor for the square lattice tensor network. And T also contains the many rank 4 tensors and many tensor contractions. But it's possible to evaluate DE approximately using tensor renormalization. And this figure shows a tensor renormalization of environmental tensor DE. And in this figure, two tensors in environmental tensor is renormalized into a single tensor. So E of n denotes the environment tensor at nth renormalization step. And so these T's are tensors at nth renormalization step, Tn. And by using projectors Un, these two Tn's is renormalized into Tn plus 1. And so these tensors are Tn plus 1, but this part is not renormalized. So this part is made of Tn and Un. And so renormalized environmental tensor is a product of En plus 1 and Un and Tn. So we found this recurrence relation from this figure. So En is obtained by solving this recurrence relation. And once En is obtained, the isometry can be updated from using the environmental tensors. So firstly, we define this Xn from this, and so diagrammatically Xn is expressed like this, and Xn is made of environmental tensor Tn and two Tn's and Un. So one Un is removed from the whole tensor network. So the partition function itself is given by Un and Xn. And so Xn is given, then we perform the SVD for this Xn. So two unitary matrices U and V are obtained from the SVD of X. So this projector is updated from these two unitary matrices, and by using this updated unitary projector, G is approximately given by singular values of X. So this U includes this U includes the information from the environmental tensor. Okay, so and this summarizes the renormalization step of higher order SRG. The firstly, the Tn and Un are generated by the normal higher order TRG, and Tn and Un are the initial set of the tensor and isometries at the nth renormalization steps. Then we use forward and backward algorithms that repeats this one and these two steps. The first step, the environmental tensor can computed by solving the recurrence relation, and the environmental tensor is obtained. Then two procedures are repeated. The UN is updated by using this procedure, and then U is updated. The renormalized tensor T is updated by using this projector. So repeating these two procedures, the information of the influence of environmental tensor is is incorporated into the TN. Okay, so by using these two steps, the accuracy is accuracy of results is improved. And this figure shows the numerical results of SRG schemes into dimensionalizing model. And blue and red are the results of SRG and HOSRG. And the SRG schemes drastically improve the accuracy of TRG and HOTRG. So, okay, so and I proposed that the SRG scheme in the triad SRG in 2 dimensions, and in 2 dimensions, triad representation of a rank 4 tensor is a product of 2 rank 3 tensors. So 2-dimensional triad tensor network is just a honeycomb tensor network. So 2D triad TRG is the same as that the HOTRG like renormalization for honeycomb lattice tensor network. But without any improvements, the isometry U and the new triads are constructed by ignoring the influence of environmental tensors. So we prepare the environmental tensors by using rank 3 tensors, and the HOSRG like recurrence relation was given by the triad and rank 3 environmental tensors. Then the cost of the triad SRG is proportional to d to the 5th, which is smaller than that of HOSRG. And this figure shows the numerical results of free energy. And red points are the results of HOTRG, and blue ones are HOSRG results, and greens are triad TRG results, and yellow are triad SRG result. As can be seen in this figure, for a fixed D, the HOSRG shows the best performance. Okay, so however, this figure shows D-cut dependence on this figure shows the time, real computational time, and the x-axis is D-cut. So from this figure, the HOTRG and HOSRG scales with d to the 7th, and the computational time of triad SRG and triad TRG scales with d to the 5th. These dependencies theoretically reproduces the theoretical expectations. And this figure shows a relative error of free energy against computational time. For fixed computational time, the triad SRG shows the best performance. So the SRG method effectively works with the triad TRG method. Okay, so so if you have a question, please ask me a question. I want. Okay. So
Does anybody have any questions? Okay, no questions at the moment. Daisuke, please go ahead. There are no questions from this side.
Okay. So, yeah, but this is I talked everything. I talked everything that I wanted to talk. So, if you have any questions, please ask me.
Okay, great. So let's all thank Daisuke for the lectures and talk. So any questions, any general questions from any of the lectures? Yeah, Rich, please.
Are you posting your slides? Are you posting your slides on the Slack channel?
Okay.
That's my question.
Question? No, no, but it's possible to post it.
Good.
Okay, so yeah, so let's
Hello.
thank Daisuke Kadoh. Oh yeah, there's a question. Okay, yeah, Omega, please.
So yeah, I'll ask one thing. In the last slide, you mentioned something about random sampling. So as far as I know, the tensor network method basically is a deterministic method. So adding random sampling is like you are moving towards the probabilistic approach of it. So if you could comment on that.
Which slide?
The very last one, 114.
Here? Sorry, here?
114. Yeah. About the 4D gauge theory, random sampling. So I was just a bit confused that as far as I know tensor networks, I think it is a deterministic approach. So adding random sampling means basically you are adding the probability to it. So if you could comment something on this one. Although you did mention that there are further improvements that needs to be done, but still.
Random sampling approach, I think we well approximate the Hall measure at least in 2 dimensions and in 3 dimensions. So, so I think it also works in 4 dimensions. So, but of course, it's very effective for strong coupling region. So in weak coupling region, some improvement of random sampling will be important. But basically, the random sampling method with some improvement will be useful to study 4D gauge theory using the TRG method.
Okay, so let's all thank Daisuke once more.
Thank you.